All right, guys, so this is going to be a walkthrough of some of the basic ideas that we use when we're talking about Fourier series. So the position that we're in right now is that we know what a Fourier series is, but we don't actually know how to compute one. So let me write down what I mean by that. We know that f of t is equal to the sum from n equals minus n to n of cn e to the 2 pi I n t is a Fourier series. What we don't know yet is how to directly compute the coefficients Cn. Now, it's still the case that we can work with Fourier series if we're working with trig functions. And the reason that we can do that is because we can take trig functions and turn them into complex exponentials. So if I wanted to do a Fourier series for, say, a combination of the sines and cosines, so let's say that we're working with f of t is equal to the sine of 2 pi times 80t and the cosine of 2 pi times 100t. Now the reason that we're splitting off the 100 and the 80 from the 2 is because this number is what tells us the frequency that that sinusoid works at. So in the case of the first sine, this is going to be an 80 hertz sine signal, and this is going to be a 100 hertz sine signal or cosine signal. And what that means is that that function repeats itself 80 times in the space of every 1 second. Remember that the unit on hertz is 1/seconds. So if you wanted to write a Fourier series for that function, the easiest way to do it is actually to replace the sine and cosine with their definitions in terms of the complex exponentials. So what we're going to do is use the formula sine theta is equal to e to the I theta minus e to the minus I theta over 2I, and that cosine theta is e to the I theta plus e to the minus I theta over 2. And with those substitutions, we can take f and we can break it up into complex exponentials and rearrange it. After all, that's what we mean by a Fourier series, is a function represented in terms of complex exponentials. Okay, so if we do that, what do we get? We're going to get f of t is equal to e to the I 2 pi 80t minus e to the minus I 2 pi 80t all over 2I. That's the sine. Plus this cosine term, which looks like cosine e to the I 2 pi 100t plus e to the minus I 2 pi 100t all over 2. And if you take that and you break it up and you rearrange it, what you're going to get is something that looks like this. This will be equal to, and what usually the way that you like to think about these is you arrange them from lowest frequency to highest, starting with the lowest negative frequency and moving up into the highest positive frequency. So the most straightforward arrangement of this is going to be 1/2 e to the minus I 2 pi 100t, because that's the term that goes with n is equal to minus 100 hertz. Remember that the negative frequencies just travel in the opposite direction as the positive. Then you're going to have the term that goes with the negative 80 right here, minus 1/2I e to the I 2 pi 80t. Then we're going to have the 80t term, the 80 hertz term right here, 1/2I e to the I 2 pi 80t. And then finally the last term that we haven't done yet, which is 1/2 e to the I 2 pi 100t. So this is a Fourier representation, but it's not in the best possible form yet because we've got this I running around in the denominator of a fraction. And we're writing a complex number. Typically what we want to do is put it in the form a plus bi. And so we can use the trick that I, or 1 over I, is just equal to minus I. You can see that if you multiply the top and bottom by I, you'll get I over I squared, which is I over negative 1. And so the most straightforward way of writing this is going to be to rewrite this as 1/2 e to the minus I 2 pi 100t plus 1/2 I e to the I 2 pi 80t minus 1/2 I e to the I 2 pi 80t. There's supposed to be a negative here. And finally, 1/2 e to the I 2 pi 100t. And we know which coefficients these are because we know the frequency, right? Though the n's come from the frequency of those particular complex exponentials. So the frequency here is 100, or negative 100. So this is the c minus 100 coefficient is equal to 1/2. And the c minus 80 coefficient is 1/2 I. And the c80 coefficient is minus 1/2 I. And the c100 coefficient is also 1/2. And we could verify that we believe the work that we've done first by looking at the relationship between the different values of c, the different coefficients. Remember that it's supposed to be the case that ck is equal to the complex conjugate of its negative coefficient. And we see that right here. C minus 80 is 1/2 I. And if I take the complex conjugate of that, I get the complex conjugate of 1/2 I, but that's just minus 1/2 I, which is C80. So at least we believe that we've done that part of it correctly. And so this is the Fourier series. Now we can say a little bit more, which is that we could write down the Fourier transform of f. So remember that the Fourier transform, f hat, is a function that takes in frequencies and spits out Fourier coefficients. So f of minus 80 is c minus 80, which I know, 1 over 2i. And f hat of 80 is equal to c80, which is minus 1/2 of I. And these numbers that the transform produces, these complex numbers that are the coefficients of a Fourier series, those are called the spectrum of f. So the spectrum of f is this arrangement of complex numbers, complex coefficients that correspond to given frequencies. And if you know the spectrum of a function, then you already know what the oscillating parts of the functions are and what frequency they oscillate at, but you also know how to reconstruct the function because you know the coefficients of the Fourier series. So f and f hat contain the same kind of information. I should point out here that f takes in a time and spits out an amplitude. So f is called a function in the time domain. F hat takes in a frequency and spits out a Fourier coefficient. So f hat is a function in the frequency domain. These are terms that get thrown around, but they're transforms of each other, which means I can go back and forth. If I know one, I can find the other. Okay, so that should help you find, say, everything that we've talked about here is relevant to problem 3 on homework this week. And you can actually probably use some of the stuff about periodicity to talk about problem 2, but let's talk about what it means for a function to be periodic first. So one thing that you're allowed to assume is that the sine of x is periodic with period 2 pi. You just get to assume that, okay? Something you've learned in trig, so you know that already. If you put anything else there inside there with the sign, what you're doing is you're changing the period. So if you put the sign of, say, AX in there, then the period is equal to 2 pi divided by A. Okay. So here's a quick question. What is the period of the sine of 8 pi x? Probably put the question mark outside the parentheses. And the answer is, well, that's the a value right there. So you know that whatever the constant that's been multiplied by the variable, you take 2 pi and you divide it by that. And you get, in this case, a period of 1/4. If you were going to plot that, what that would mean is that in the space between 0 and 1, this function repeats itself 4 times. The sine of 8 pi x does an entire cycle of the sine, and then another entire cycle of the sine, and another entire cycle of the sine, and another entire cycle of the sine. So this does itself 4 times between 0 and 1. That's what it means to have period 1/4. So the gap from here to here is 1/4 wide. It can do that 4 times between 0 and 1. And that's actually why the frequency of a function is the reciprocal of its period. So frequency is 1 over the period. And so part of the reason why we're adjusting these functions so that they have a base period of 1 is so that it's very easy to read off the relationship between frequency and period. So the frequency of this function is 4 cycles per second. Well, cycles aren't a unit, and 1 over seconds is called hertz. So we say 4 hertz. So the sine of 8 pi x is periodic, or has frequency 4 hertz. So how would we look at a combination of periodic functions? So this is relevant to question 2. Well, suppose I just wrote 2 of them down. Suppose I give you the sine of 4 pi t, and then I add it to the sine, say, of 7 pi t. This function has period 2 pi over 4 pi, which is 1/2. The next one has period 2 pi over 7 pi, which is 2/7. Is the resulting sum also periodic? That seems like a basic question to be able to answer. Is this function periodic? Its pieces are periodic. Is it periodic? So one way to think about this is, do they ever land in the same place at the same time? Can you ever get the sine of 4 pi t to be equal to the sine of 7 pi t? Or if I do periods that are all 1/2 of a unit long, does it ever land exactly on the same place as a function that has periods that are exactly 2/7 long? And the answer is going to be yes, if you can find a way to multiply 1/2 by a number and multiply 2/7 by another number, and they land on the same number. If you can do that, then these functions will be periodic, and you'll know something about what the period is. So what do I mean? Well, just imagine that you have the sine of 4 pi t doing its part. So every 1/2 of a unit, 1/2, 1, 3/2, 2, 5/2, 3, 7/2, 4, and so on. This thing is going like this. So we have the sine function, so it's kind of going sine, 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 so on. Okay, so meanwhile, what is the other function doing? Well, there's 1, there's 2, there's 3, there's 4. So the other function is repeating itself every 2/7 of a unit. So it hits itself at 2/7 and 4/7 and 6/7. Then it skips over 1. If it had landed on 1, then it would have matched up and landed in the same spot as the other. And that would have been a place where the two functions overlapped perfectly, and then the whole pattern would start over again because they were both starting fresh. But they didn't land at the same point, so we've got to keep going. 8/7, 10/7, 12/7, and then all of a sudden we hit 14/7. Well, at 14/7, this function lands exactly on 2. And at the same time, this function also lands at 0 at 2. So they started at 0 together. And then they land at 0 simultaneously at t = 2. And that means that's actually their shared period. So the shared period of these two functions is 2. Is there any way that we could have figured that out by looking at these two numbers up here? What is the smallest number that you can, that is a multiple of both of these numbers? So you want the least common multiple, and they're fractions, so you have to modify your definition a little bit. So you want integer multiples of the period. Okay. So that's a hint for number 2 right there. You should be able to show me that if I gave you 2 different fractions for periods, that they land at the same spot. The first spot that they land simultaneously at is their smallest integer multiple, which is going to be the least common multiple. So in this problem, as soon as we land the 2 functions back at the same spot, it's like the whole pattern starts over again. And so the combined period of f of t is equal to the sine of 4 pi t plus the sine of 7 pi t is 2. This has period 1/2. This has period 2/7. Their combined period is 2. So f is periodic of period 2. And the point of question 2 is, can you figure out a way to do that generally for any fraction without having to do what we just did right now? Instead of starting with a specific fraction like 1/2 and a specific fraction like 2/7, can you figure out a way to put those together so that you can just write down what the period is by looking? Okay, now it's not the case that the sums of periodic functions have to be periodic. And the reason that's not the case is because there are numbers that never overlap each other, no matter how many times you multiply them by an integer. So if you had something like 2, and you started multiplying it by any integer you wanted, it can never be equal to 2 times the square, to say like the square root of 3 times a different integer. You can't do this. There is no possible way this can happen where, say, this is some kind of irrational number. What that means is there'll never be a least common multiple if you have a function that has period 2 and a function that has period root 3, because there's no integer multiple of both of them. It just doesn't exist. I mean, there's a contradiction here. If you could find an n and an m so that 2n was equal to the square root of 3 times m, then it would mean that the square root of 3 would be equal to 2n over m. That's a rational number because it's a fraction. But root 3 is irrational. It doesn't have a rational expression that expresses it, right? And so that means that this is impossible. So when you have mixtures of functions that have rational periods with functions that have irrational periods, and you add them together, you don't get anything periodic out the other side. You get this crazy chaotic behavior instead. Okay, so there's some problems you might think about or some things you might think about in question 2. So that means that, so 2a and 2b are questions where this idea is going to work. So 2a and 2b kind of follow the idea of, can you show me that at the least common multiple of n and m or p and q, that the two functions that you're looking at land at the same point and start their cycles over again simultaneously. For problem 5 is easier than it looks. So the idea in problem 5 is that you just have to know what the definitions of even and odd are. So a function g of x is even if f of x is equal to f of minus x for all x. This is also called symmetry across the y-axis. And so 5a asks you to show that the function fe of x is equal to fe of minus x. This is what you're to show. Okay. A function is odd if f of x is equal to minus f of minus x. Or some people like to write minus f of x is equal to f of minus x. An example of this would be the sine. An example of this would be the cosine. Or say a function like x squared or a function like x to the third. Those are functions that have this property. This is called symmetry about the origin. So what I'm asking you to do in question 5b is to show me that fo of x with a negative in front of it is equal to fo of minus x. That is, a function is odd if you can pull the negative outside. So I've given you the definition of fo. From that definition, you should be able to show me that that property holds. So this is what you're to do here. Then for part C, it's a basic algebra question. And for part D, you just use the formulas. So 5D, you just use the formulas from parts A and B. Okay, so for the complex number questions, this is question 6. This is about complex numbers. Generally, when you're working with complex numbers, if you don't understand what's going on, you rewrite the complex numbers in the form a plus ib. So if I ask you to do something like, show me that z times z bar is equal to the absolute value of z squared, the way that you do that is you just write down z is equal to a plus ib and do algebra. So what is z times z bar? Well, that's a plus ib times a minus ib. Remember, the conjugate of z reverses the sign of the imaginary part. Then you can FOIL this out. You would get a squared plus aib minus aib. And you're going to get a minus I squared b squared. But minus I squared is the same as minus minus 1. So this all turns into a squared plus b squared. So that's this half. How do I compute the absolute value of a complex number? Well, the absolute value of z is equal to the square root of a squared plus b squared. So the absolute value of z squared is a squared plus b squared. So since the absolute value of z squared is equal to that, and z times z bar is equal to this, these two things must be equal. That's the sort of thing I expect you to do in 6a and 6b. In 6b, it's actually easier to show what's happening if you use the polar form. So let's talk about that for a second, the polar form. If you have a complex number written down as z is equal to r e to the I theta, and you take its conjugate, remember that when you have a complex conjugate applied to a whole brick of stuff, it goes inside and hits all of the pieces individually. Now the radius in a polar form is a real number. And whenever you take the complex conjugate of a real number, you just get back the same number unchanged. There's no imaginary part to negate, right? So this is just r. Now the next thing that happens is when you have complex conjugate outside of a function, you can take it and put it inside. So the complex conjugate of e to the I theta is actually equal to e to the complex conjugate of I theta. And that's just r e to the minus I theta. Because remember, what complex conjugation does is it negates the imaginary part. From the standpoint of rotations, what this is doing, if you had a point, say, this is the circle of radius r, and you had a point theta, so that this point right here was r e to the I theta. Remember, that's how I want you to visualize these things, as sort of they're on some kind of expanded map of the unit circle. Then what the complex conjugate is actually doing is just producing the negative theta point. That's supposed to be negative theta. So that's going to be useful in 6b, for example. It's very easy to show that the division rule holds if you do it with the polar form. So you might use polar form on 6b. So the last thing that I want to talk about in this sort of brief video of examples and hints on the homework would be to look at the stuff around problem 4. So problem 4 says that you have two sinusoids with the same frequency but different amplitudes or phase. So the first thing you need to do is be able to write down what that means. So if they have the same frequency but different amplitudes or phase possibly, what could that mean? Well, let's just write two of them down. So f of t could be a times the sine of nu. In fact, we can work on 2 pi if you want. So we could write 2 pi nu t plus phi. There's one sinusoid. And then we should say nu 1 and phi 1. And let's call g of t equal to a2 sine of 2 pi nu 2t plus phi 2. Now we want these to have the same frequency, and so that means instead of a nu, we could just write n here in both cases. Same frequency. And in a generic sinusoid, that's how you write the same frequency, is that the frequency term is identical, right? So these things being the same means that you have the same frequency. So what happens when you do f plus g? What's the result? So here are some possible answers. You could get a not periodic function. Now these aren't, only one of these is true. I'm trying to give you some ideas you might think about. So maybe it's not periodic. Maybe it's periodic with a different period. Maybe it has what are called beats, which is to say that because the phase is different, maybe the peaks of the sine waves collect up and then spread out, so they cancel and collect up and spread out. So maybe you get what are called beats. Maybe you either have a new sinusoid of the same frequency or 0. So the idea here is to think about when you take f and g and you add them together, what possible outcome could you get? It's only one of these. So, or I guess I'll say E, none of the above. So one of these is true. So which one is it? And the hint is that you should be able to take this. So this complicated looking mess right here has an exponential representation. that you can actually write f of t is equal to a sine 2 pi nt plus phi1, and you can rewrite that using the definition of sine, that sine of x is equal to e to the ix minus e to the minus ix over 2I. You can take this definition and rewrite both of those sinusoids. And I want to know, when you're all done with it, do the e to the ix terms have the same frequency as the sine functions that you started with? Does this form have e to the I 2 pi nt in it? Because if that's all that it has inside, then the frequency is the same. But if it does not have e to the I 2 pi nt inside of it, then the frequencies have changed, and I want to know how they change. So my hint on number 4 is convert the functions into generic sinusoids, write them down in terms of their complex exponential representations, and then just do algebra to try to add them together. All right, so I think that's a reasonable place to stop this set of examples. I'm happy to compute more things here if I find out that you guys have additional questions. Most of the rest of the homework is actually pretty straightforward. For example, number 1 is just doing standard sort of power series manipulations. If you're having trouble with this stuff, please come to office hours so I can kind of guide you through it. A lot of the structure of the sinusoids and trigonometric series that we're talking about now are going to inform the way that we're thinking about more complicated functions later. So we have to have a really strong grasp on the way that sinusoids work to get a feel for what it is that Fourier series and the Fourier transform are allowing us to do. Okay, so I will talk to you soon. Thanks.